I'm William Neal. I teach a course in fish biology here at Texas A&M, Wildlife and Fishery Sciences 417. The purpose of this presentation is to introduce an important tool that I use in that course. It's a simulation model that I call Ecofish. Here's the place of biology of fishes in our overall undergraduate curriculum in the aquatic area. We've got about a dozen courses here. 4 of these, including biology of fishes, are considered core. They're limnology and ichthyology and fisheries management, as well as biology of fishes. You can see the subject matter range of each of these courses indicated by the vertical bar. My course, for example, spans from environment and habitat up to and including some population biology, but most of the emphasis in the course is on the relationship between environment and the individual fish. This is sort of the way I see the relationships. Environment is linked to physiology of the individual fish through exchanges of energy and materials and information. Those exchanges, of course, go both ways. The physiology, in turn, dictates certain behavioral responses on the part of the fish, and an important subset of that behavior feeds back to affect future environment. These I call enviroregulatory movements, or perhaps you might know them better as habitat selection behavior. That environmental issue is a complicated one, and this slide illustrates the degree of that complexity. Here's a graph of, I started to say real world environment, but it's only quasi-real world. It's an aquaculture pond down on the Texas coast at Corpus Christi at the Marine Development Center. And what I've got graphed here are 4 important aquatic variables, dissolved oxygen, temperature, salinity, and pH, against time. And the time is fairly extensive. It's 13 months, 9,520 hours. I think these data were collected 3 times a day. The y-axis is different for each variable, but let's just take a look at DO. The scale there is from 0 to 20 parts per million. DO is the one here in green. And you can see that DO is highly variable on a diel basis over the course of this 13-month period. At some points here, the amplitude is almost 12 parts per million. Temperature shows its normal annual cycle here, being high in the summer and lower in the winter, with some pronounced cold fronts, the evidence of cold fronts. Salinity, this is a hypersaline system, and you can see some rainfall events that cause precipitous drops in the salinity, which typically was up here around 40 parts per thousand. pH is relatively stable but high at about 9. This system is well buffered. Well, given that environmental variation going on, how do you make sense of that in terms of the biological impacts on organisms? That's something we've been trying to do for at least a century, I guess. Half dozen years or so back, my good friend and colleague John Miller and I got together down on the Texas coast and spent several days talking about this issue and thinking about it, and we finally decided that the key might be something done by this fellow, F.E.J. Fry, who for many years was at the University of Toronto. This monograph was published in 1947, and in it Fry said that the effects of environment on the animal are through its metabolism. That is, environment affects activities of the organism, activities like growth and locomotion, only through the metabolism. Well, John and I got to thinking about that, and we decided it might be the key to understanding the system, and that's where it all started. Before I talk about where we took that, let me tell you about Fry's ideas. Fry said that all of environment can be categorized into 5 sets of interacting effects, physiological effects on the organism. Controlling factors like temperature and pressure, and pH, set the pace of metabolism. Limiting factors are resources like dissolved oxygen that, when deficient, depress the maximum rate of metabolism. Masking or loading factors are factors like extreme salinity that cause the animal extra work just to maintain itself. Lethal factors destroy the organism by completely interdicting metabolism. And finally, directive factors guide the animal through time and space, through time and its adaptations to environmental factors physiologically, and through space as distributional responses. And those distributional responses are particularly important because they feed back through locomotory activity to put the animal in a different place where environment is different and therefore would have different physiological effects in the future. A bit more graphically, you can think about the rate of performance as a function of the availability of resources, performance being metabolic rate, for example, and resource being dissolved oxygen concentration. And you could recognize three levels of performance. There's the biological minimum level, like standard metabolism. There's the routine level of metabolism, or the normal level that you might think of as, in many cases, the ecological minimum. And then finally, there's this maximum level of performance, or the active metabolic rate, which sets the absolute upper limit on performance. Notice that the routine and minimum levels of performance are relatively independent of the resource supply over much of the domain of resource supply. But the active or maximum level of performance rises steeply as supplies rise until finally it asymptotes at high levels of the supply. You can see easily the role of Fry's factor classes here. Controlling factors affect both the slope of the increase in active rate as a function of resource supply as well as the minimum or standard rate of metabolism. Masking or loading factors raise this minimum. Limiting factors depress this maximum. Directive factors alter the routine level of metabolism as well as positioning the animal along this resource supply axis. So when the animal is successful in response to directive factors, it moves to the right here towards higher levels of resources, which gives it higher capacity for performance. The difference between maximum and minimum levels of metabolism Fry called metabolic scope. We've subsequently defined the difference between maximum and routine levels as being maximum scope for growth, and the logic there is that the difference between routine and minimum is routine activity, mostly locomotory activity, leaving what's left really available for growth. Lethal factors, as this hammer indicates, simply shatter the system, destroying it. Well, that's Fry's physiological classification of environment. And what we set about doing was trying to implement Fry's scheme using computer technology, making use of the 40 years of additional information that was available after Fry's time, or after the 47 monograph. And we succeeded, I think. And the end of the story is Ecofish that I'll get to. But before I get to that point, I want to talk about the software that we use to build a simulation model. It's a very handy and convenient to use systems simulation package called Stella. Here is sort of my lead-in to the Stella demonstration that I want to do for you. What I've got here is a simple model of hydraulic head and flow. Imagine, if you will, this system. Here's a tank full of water. For convenience sake, you might think of it as being a meter square in cross-section and several meters deep. And what we're suggesting is that the hydraulic head of the water influences the rate at which water is discharged through this opening here at the bottom of the pipe. So now I'm going to break from my PowerPoint presentation and go to Stella and actually build this little model for you to watch as I build.